Hello, everyone. So we've talked about the fact that quantum mechanics is a probabilistic theory. It doesn't tell you exactly what's going to happen in any particular measurement, but it allows you to know what's the probability that I'm going to get a certain thing when I do a measurement. So before we can dive into quantum mechanics, we need to refresh our memory about probability and statistics. So I'm just going to talk about some basics in this pre-lecture, just about sort of how probabilities have to be normalized, how to calculate averages and squared averages, and then the variance and the standard deviation. So I have here a sample data set. For example, this might be generated if I asked all the students in the class to provide their height. And I make a histogram of the students versus their height. So one person is 5'2", that's 62 inches. Two people are 5'3", that's 63 inches, and so on. So if I took a student from random from the class, what's the probability, let's say, that they have a height of 5'4"? I would write that something like this. P, and I'm just going to use inches here, so P 5'4", that would be the probability that if I select someone at random, that their height is 64 inches. That is obviously just the number of students who have a height of 64 inches divided by the total. So that's 3. And then the total number here is 47. If you add up all those, the total number is 47 students here. Okay, so kind of obvious. You could ask a little bit more tricky question. What's the probability that the height is between 5'4" and 5'7"? So that would be 64 inches less than or equal to h, less than or equal to 67 inches. Let's say if I picked some student at random, what's the probability that that student would have a height that lied in this range? I would add these probabilities. So I'd take the probability that someone has 64 inches plus the probability that they have height 65 inches plus 66 plus, and that is equal to, I can just count here. This is 3, this is 2, number with 66 is 4, and this is 5. Divide by the total over 47. It's 14 over 47. Okay, probability should also always be less than 1. This is less than 1. Now, what's the probability that if I pick somebody at random that they have any height, I should get 1, right? Of course, everybody in the class has some height. So you see here I added up the probabilities of, these particular heights, 64, 65, 66, 67, and I got this number 14 out of 47. But of course, if I added up all of the possible heights, I'd better get 1, 100% probability that a student selected at random has some height. So that's one way of saying that the data set is normalized. When we say the word normalized, we mean that the probabilities sum up to 1. So to have a properly normalized data set, or when we start working with continuous distributions, a normalized distribution, means the probabilities have to add to 1. So I must have that if I add up the probability over all heights, h equals, let's say, 0 to infinity, that had better be equal to 1. Probabilities sum to 1. Probabilities sum up to 1 for it to make any sense at all. How about averages? What's the average height of people from this data set? Well, you know how to do that. I'm going to denote it as using the angle brackets. Angle brackets mean average height. You know how to calculate an average. You've known how to do that for years. You just add up all of the heights and divide by the total. So I would say there's one person with 62 inches. There's 2 people with 63 inches, so I'll write them both, 63 inches plus 63 inches. There's 3 people who have a height of 64 inches, so I'll write all 3. And you just keep going. Divide by the total, which is 47. Okay, that's how I would calculate the average. That's a kind of grade school way of calculating the average. Now we can write this a slightly more complicated way. So I could write 62 inches divided by 47 plus, you see there's 2 people who have height 63 inches, so I would write 2 over 47 times 63 inches. And there's 3 people who have a height of 64 inches, so I would write 3 over 47 times 64 inches. And keep going. This is the same thing, right? Just rewritten. And you notice what's happening is this here is the probability that somebody has height 64 inches, right? This is the probability that someone has height 63 inches. So what I'm really doing to calculate this average is I take the height, I multiply by the corresponding probability that somebody has that height, and then I add those up. So here's a more compact way of writing that average. I'm going to sum up from h equals 0 to infinity, all the possible heights, from h equals 0 to infinity. The probability that somebody has that height, so that's p of h, times the height itself. This is the average height. Okay? It's not equal to 1 because of this thing. If that wasn't there, it would add up to 1, but I'm taking the probability times the height, and that gives me the average height. Okay, when you're dealing with data sets, a lot of times another quantity that shows up a lot is the squared average. So that means, like, what is h squared, average of h squared? If I square all of the heights, add them up and divide by the total, that's what I'm calculating here. That would be, 62 inches squared. And then there's 2 people who have a height of 63 inches. I square that. And then there's 3 people who have a height of 64 inches. I square that, and I keep going. Add them all up. Divide by the total. And there's 47. Once again, you're seeing that, this number here, 2 out of 47, is exactly the probability that someone has a height of 63 inches. And this one here, 3 out of 47, is the probability that someone has that height. So I can write this summing from h equals 0 to infinity, the probability that someone has height h times h squared. This is the average of the squares of the height, h squared. Once again, it doesn't add up to 1 because of this thing here. If that wasn't there, it would add up to 1. You're maybe starting to notice a pattern. If I want to average something, so h squared here is what I'm averaging, it multiplies the probability here and then add up all the possibilities. So average h squared, take your probability, multiply by h squared, add them all up. Average h, take your probability, multiply by h, add them all up. You can generalize this in a kind of obvious way. If you want to average any function, let's say you're averaging some function f of h, what I should do is just kind of, by analogy, take the probability that somebody has the height h, multiply by f of h. So this is the general formula. Let me get rid of that to buy myself some space. Now the last thing I want to talk about, or some things I want to introduce to you, is something called the variance. It's a quantity, and it's defined to be the Greek letter sigma squared. So sigma squared is called the variance. And here's what it is. It looks kind of funny when you see it to start. Okay, so this is, I'm going to write it something like this. So what does this mean? For each height, you find out how far away it is from the average. So h minus the average h. This is how far away each height is from the average. Some will be above the average, some will be less than the average. And then I square that in order to account for the fact that some are negative, some are positive. So I'm basically, this thing in here is measuring how far away each one is from the average. And then I average that. So there's another average angle brackets outside, meaning I'm taking the average of the difference from the average, if that makes sense. So we write that sometimes as delta h squared. It's a measurement of how spread out your distribution is. So if your variance is large, it means that you have a lot of data points which are far away from the average. If everything is very clustered around the average, you have a small variance. I'm not going to prove it to you here, but it is fairly easy to prove that here sigma squared is equal to the following thing. Average of the squared heights minus h, the average squared, minus h squared. So this you can see the notes if you want to see how that proof goes. And the first time you see this, you're sort of surprised. You're like, why is this not the same as this? So the question, this is you square it first and then average. This is you average it first and then square that. So one is you're doing the averaging first before the squaring. One is the squaring first and averaging those. So the order matters. Whether this 2 is inside the brackets or outside means something different. Okay. Finally, I'm going to introduce the standard deviation. And it's very easy. Standard deviation is just sometimes written as sigma, which is obviously the square root of the variance, sigma squared. So it's the square root of h squared minus h squared. And again, that standard deviation, just like the variance, is a measurement of how wide the distribution is or narrow. So is your distribution very spread out, or is it very clustered close to the average? This is a big standard deviation. That's a small standard deviation. So this has been a review of some very simple concepts in probability and statistics. We talked about how to calculate probabilities. We're using this notation here, P of h, to mean the probability that somebody had selected at random has height h. If you add up all of the probabilities, they should sum to 1. If you want to average something, I multiply the probability times the thing I'm wanting to average and add all those up. So this is the average height. This is the average squared height. This is the average of any function of height. And then we introduce the idea of the variance. And this formula here is maybe the most useful one. Average squared minus the squared average. And then the standard deviation is the square root of that. So this has been a discrete data set. People have particular heights in inch increments. In class, we're going to start talking about what if I have a continuous variable. Of course, height is actually a continuous variable. People can have any height. How do we handle that? How does this generalize? So we'll pick it up there in class. Thank you for your attention, and see you all then.